You already know the answer, right? You shoot a laser pulse out, wait for it to bounce back, and measure the time. No need to watch the video. This is usually the part where I lean in and I tell you that you're wrong. But don't worry, you're only half wrong this time. That is indeed one way to measure distance. It's called LiDAR, which is a ridiculous backronym that barely means anything. Using LiDAR these days is like using AM radio. It has a use case, but I prefer FM radio. Okay, I haven't actually tuned an FM radio in a decade, but FM lasers, that's where it's at. Last time, I walked you through a simple laser to measure speed. So let's talk about how we can use the same setup for distance. If you're like me, you hear your calculus professor yelling in your head right now, distance is the integral of velocity. For this sensor though, they're wrong. We're not summing the velocity over time to get distance. This is a completely separate and independent measurement, and it's also completely different than LiDAR. If you haven't seen the video on speed measurement, go watch it first. You'll be a little lost otherwise. When I first found out about this trick to measure distance, I felt so stupid for not thinking of it myself. It's like a magician's sleight of hand. It's so hard to spot, but it's so simple once you've seen it. Once again, we're gonna do this magic trick with no extra equipment, just a simple laser. Now, let's give LiDAR its due. It works great for measuring distance sometimes, but it has some major limitations. When we discuss LiDAR, we usually mean time of flight measurement. This may surprise you, but light travels fast. If you want to measure something 30 meters away, you have about 200 nanoseconds to measure it. That's right, we're using meters, not feet. This is America, not Japan. There's no need for the imperial system here. We invented driving and the Wally mobility scooters, so we don't have to use feet. Now, what were we talking about? Oh, light. Light is fast. 200 nanoseconds for a 30-meter distance. And to measure that digitally, you'll need to be able to sample around 10 gigahertz to measure at that distance. This is difficult, but it's doable. Smart people make incredible sensor suites capable of this. But what if you need to measure 1 meter away? Well, that light is coming back now in 7 nanoseconds, so I hope you can sample at a few hundred gigahertz. And even if you can do that, if you're off by even 1 nanosecond, the error in your measurement is 15 centimeters, which is 15%. The point is, time of flight, much like airplane flying, is best suited for long distances. There is one company combining time of flight LiDAR with Doppler shift measurement, but more on that later. There is another way to solve this problem that works best at short distances. It's known as triangulation. Here you can see how that works. A laser hits a surface and then bounces back through a lens and onto a linear light detector, which detects the location of the laser reflection. The lens is angled to keep the light detector in the focal plane using the Scheibenflug principle, coined after this handsome devil, sorry ladies, he's taken, by the grave. This method works super well in the opposite conditions as LiDAR. It's meant to be short range. In fact, even 1 meter is starting to push the upper limit. It also has a few other limitations. First of all, it breaks our cardinal rule. It needs extra equipment, the lens and the photodetector. You also have to filter the ambient light out or do modulation on the laser and recognize that pattern in the photodetector, which would break our velocity measurement that we came up with last time. So then our remaining option is to use the same method as before, a self-mixing laser. This will combine the benefits of LiDAR, no extra equipment needed, with the benefits of triangulation, working at a wide range of distances, even short ones. The only disadvantage is we're gonna have to be a little bit clever, but we can reuse the same principles we already discussed. Remember how before we were looking at this wave, and we saw how as the target moves, the laser jumps to realign itself every half a wavelength? Well, that phenomenon is all we need to measure distance. Let me show you how. Okay, Remember I said it's a trick that's right in front of you? Let's watch the replay. Can you guess how we do it? Okay, let me add another wave to the chart. I told you before, the solution is always to draw more waves. I've drawn a blue wave right on top of the red wave, which is why it looks gray. The blue line represents the nominal or ideal frequency. It's the frequency the laser would like to be at. It's the frequency that keeps the laser perfectly aligned with the cavity. Or it's what the laser would send if it was just shooting off into space with no target. Whenever a fringe happens, it's caused by the red line jumping towards the blue line, trying to stay as close as possible to the nominal wavelength. What's causing these fringes is that I'm shifting the laser cavity to be slightly smaller or larger, and this is changing the nominal frequency. I want you to count the number of fringes that happens when I shift the frequency by a certain amount. Let's count. 1, 2, 3, 4, 5, 6, 7. We have 7 fringes when we shift the frequency. Now let's move the target closer. And now we'll shift the frequency by the same amount. Can you guess if anything will change? 1, 2, 3. Now we only have 3 fringes. So the fringe count changed drastically by the target getting closer to the laser. If this is a little shocking to you and it's not the obvious revelation you were promised, don't worry. This seemed a bit odd to me too until I looked at the equations. This is a rare case where I think the equations are more intuitive than the animation. A basic definition of a wave's total length and how it relates to the wavelength is given by this equation. This is just an obvious fact, it's the definition of a wave. But remember that the frequency of the wave is just its speed divided by its wavelength. So since we know the speed of light, we can put the frequency into this equation instead of wavelength. How did this help us? Well, the big problem in this equation is we have no way to know the number of periods. But wait, this equation means that there's some number of periods at a given laser frequency, and that there's a different number of periods at a different laser frequency. But for the same distance, the ratio of periods to frequency must stay the same. So for example, if you have 10 periods at a frequency of 1 Hertz, you're at a distance of 10. Well, 10 times the speed of light, but that's always the same for these equations, so we can just ignore it and focus on the ratio. If you're still at a distance of 10, but you double your frequency to 2 Hertz, you now have 20 periods, a change of 10 periods, which means you'll have 20 fringes by making the frequency change because there are 2 fringes per period, 1 for each half a wavelength. Now let's say you're at a distance of 100, so 10 times further away. Again, at 1 Hertz, that means you have 100 periods. If you make the same frequency change as before from 1 Hertz to 2 Hertz, you now have 200 periods. So now you have 100 more periods and therefore 200 fringes. Something interesting just happened. If you're 10 times further away, you can change the frequency by the same amount and you see 10 times the number of fringes. If you're half the distance and you ramp the frequency again by the same amount, you'll get half the number of fringes. So essentially, by ramping the frequency, we can take this single equation that has 2 unknowns, number of periods and length, and add 1 more equation. Now 2 unknowns and 2 equations. And we can now get the length, which is what we wanted to do all along. Do you remember earlier I said there's one company that's making LiDAR a little bit smarter? The company is Aurora, who bought a laser sensor company called Blackmore, and they draw a nice parallel here between FM and AM radio. AM just stands for amplitude modulation, or changing the amplitude of the waves to get the data to your radio. Frequency modulation changes the frequency to get the data to your radio. Go get in your granddad's car and tune it to an AM radio station. It's likely nowhere near as clear as FM. Why? Imagine a giant light bulb at the top of a tower, like a lighthouse. And you want to communicate data using that light. You only have 1 light, so you can't pull a Paul Revere and add a second light. So how do you send the data? You can vary how bright the light is. That would be amplitude modulation. But another way is to vary the color the light is, which is frequency modulation. Now, imagine you're trying to see that light bulb to get your data from a long way away through some heavy fog. You're gonna find it much easier determining the color than the brightness. This is what makes FM radio clearer than AM. Traditional LiDAR sends out a pulse, and it looks for the pulse to come back. It's amplitude modulated. Much like radio, the future of laser sensing is FM. So we're gonna make our measurement by modulating the frequency, observing the resulting fringes, and calculating the distance. But how are we actually gonna change the frequency of our laser? Isn't the whole point of a laser that it's a fixed frequency? Vary the power, that's how. Sorry, I couldn't wait and drag it out to tell you later. It's too clever. For reasons, the frequency of a laser changes with its power level. Even better, it does so linearly too. In fact, lasers have a parameter, the frequency tuning coefficient, which is the frequency change per current, literally measured in hertz per amp. There's a few reasons for this, but the main one is just heat. The laser will heat and cool ever so slightly, and that will cause the cavity length to change slightly, which will then cause the frequency to change slightly. So all we need to do is vary the laser power, and with a static target, we'll see fringes. The number of those fringes will vary 1-to-1 with the distance. Double the distance, double the fringes, and so on. So how do we actually count the fringes? Well, if you can't guess, then you must not have watched my first video. Our old friend, the FFT, of course. Okay, so what we're gonna do is ramp the voltage going to the laser in order to vary its power. We can't ramp forever to infinity or to 0, so we'll just ramp and then reset, ramp again, and so on. This is called a sawtooth wave for obvious reasons. The ramp rate causes fringes. I'm again arbitrarily showing 10 fringes in 1 second, so 10 hertz. However, the FFT is garbage again because of the 3-volt offset. So let's subtract the 3-volt out again, and just like last time, we get our nice FFT back. Okay, that's better. We do indeed see our familiar 10 and 20 hertz spikes, but what is this huge spike at a lower frequency, like 2-ish hertz? That is the sawtooth wave itself. See how we have 2.5 periods of the sawtooth? Well, that's what's showing up in here. And that makes sense because it's a repeating signal, so it is a frequency content. But it's not the one we care about, so we kind of corrupted our signal, and we need a way to fix it. How can we get rid of the sawtooth wave so that the 10 hertz is our biggest spike again? What we need is to not just subtract 3 volts, but to subtract out the entire power level that we're commanding or modulating on the laser. So let's approximate this shape using a low-pass filtered version of the voltage, shown here in green. The key is we picked a slow enough filter that it only includes the sawtooth but doesn't include the fringes or the noise. This is possible because we chose the modulation frequency so that we know what it will be, and we can pick the low pass frequency to match. Now we see a pretty good spike at 10 hertz. Believe it or not though, we can still do a bit better. You see these spikes in the voltage signal? They seem like fringes, but they're not. They're artifacts from the fact that our low pass filter can't instantaneously jump up. This instantaneous jump is called a discontinuity, and it's super hard to deal with. So to make it continuous, we're gonna have to make our ramp a triangle wave, where it's going up, then back down, then up, etc. What's nice is if you remember the equation, it doesn't matter if the frequency is going up or down. The frequency delta will be positive versus negative, but the fringes are simply either forward fringes or backward fringes, but we count them both the same. Side note, there actually is directionality to the fringes. They're not symmetric, and you can detect this, but we don't need to, so it's a topic for another time. So our new voltage will look like this. Subtract the green line out of it. Now we have some very clean fringes. Look at the FFT, a beautiful spike at 10 Hertz. So this means that if we have a distance of X, we get 10 Hertz. If we double it to a distance of 2X, we'll get 20 Hertz. It's a nice linear response that we can measure easily with just the FFT. So in the velocity video, we had 10 Hertz, but that was caused by a velocity. Now we have 10 Hertz again, but that's being caused by the laser shooting at a target which has no velocity, but is at a distance of 10 Hertz away. We can use the equation from earlier to translate Hertz into meters. The point is, we have the same measurement method, no extra equipment. Just by tweaking the laser power, we can measure a completely new quantity. By contrast, when measuring velocity, we had no modulation at all, just a fixed laser power. Wait. But if we don't want to modulate the power to measure speed, and we do want to modulate it to measure distance, then we can't measure both at the same time, right? What if we want to measure both velocity and distance at the same time? Well, then you're out of luck, because that's a topic for another video. At this point, you're probably thinking, how many more tricks can this guy play with this freaking laser? We still haven't talked about directionality, like whether the object is getting closer or further away. And don't get me started on how we can measure that even if the distance is not changing, because that seems insane. How could it be moving if the distance isn't changing? Oh boy, there is plenty more to discuss. I'm also planning some higher level videos on applications, industrial, automotive, consumer electronics, and more. We'll dive into the automotive applications soon and show why this is the perfect technology to solve some major unsolved problems in vehicle dynamics. Comment below which topics you'd like to see discussed first, or suggest a topic that I haven't even thought of yet. If I don't see your comment below, I'll just assume you work for an AM radio station and your angry comment didn't make it through.